So today topic is organoboranes. So this is one of the important favorite topic in examination point of view. So here the main important reagent is BH3. So here BH3 sorry. Yes. So BH3 is not available like this. So we have to make it stabilize. So in order to make stabilize, what we will do, we will treat with some Lewis base so that we can stabilize this BH3. So there are three reagents which we can stabilize BH3 with diethyl ether and in trimethyl amine and dimethyl sulfur. So here just this lone pair is going into the vacant orbital of BH3. So and this is forming a day 2 bond. Okay, like this we can make BH3 as a stable reagent. Okay, so how this hydroboration takes place, we will see. So when we have a olefin and here we have HBH2. Okay, so here there is a formation of 4-member transition state, 1 2 3 4-member transition state. After that we'll get this. So this is called hydroboration. Okay, and further it can also react with one more olefin. So here one hydrogen goes here, this BH2 goes here hydrogen, and here B, H, and this can react with one more olefin. Boron goes here, hydrogen goes here. So hydrogen, so this is trialkyl borane. So one BH3 can react with 3 alkenes. Okay, means hydroboration. And next step we have here is regioselectivity. So this is very important. After that we will see stereoselectivity. So in the regioselectivity there are two rules we have: Markovnikov rule and anti-Markovnikov rule. So what Markovnikov rule says: hydrogen attacks to less substituted carbon, so that here we can generate more stable carbocation. So this is the Markovnikov rule says. And anti-Markovnikov rule says that hydrogen attacks to the more substituted carbon, and here we generate the less stable carbocation. Okay, so these are the things we need to remember. And hydroboration follows the anti-Markovnikov rule. Okay, so when we have a unsymmetrical alkene, like here 2 hydrogens are there, here 2 alkyl groups are there. So here we have BH3. So according to the anti-Markovnikov rule, hydrogen has to attack at the carbon where less number of less substituted carbon is there. Sorry, more substituted carbon. So this goes here and B goes here, boron goes here, so that we'll get this compound. Okay, and just remember, hydroboration in the alkenes, it follows anti-Markovnikov rule, and it is a syn addition. Okay, so this is about the regioselectivity. And coming to the stereoselectivity. So coming to the stereoselectivity, here let's take this example. Here we have BH3 and B2H6. So here two products are possible. We can take this one, or we can take this also. So we know that hydroboration follows syn addition. That means both hydrogen and BH2 has to be in the same side. So in the both the cases they are in the same side. So here stereoselectivity, how? Like always remember, this BH3 goes and attacks to the double bond from the less substituted side. So here already methyl group is there, so it cannot go from the top. So because of that reason it goes from the bottom. So this is the correct answer and this is wrong answer. So just remember, if the if steric crowding is there any side, so that side hydroboration will not take place, opposite side it takes place. And we have another example, this one. So imagine that now here we cannot give above the plane, below the plane, because this is sp2 carbon. So imagine that this is above the plane, means after hydroboration. If you take this one above the plane, and hydrogen has to be below the plane and BH2 has to be below the plane. And here also here no more substituted, no less substituted. So here we can see that hydrogen is attacking here and BH2 is attacking to this carbon, because hydrogen attacks to the carbon where more substitution is there. But here we cannot say about substitution, we can say about steric crowding. So since BH2 is a bulky compared to hydrogen, so that's why BH2 attacks the carbon where less steric crowding is there. Okay, whereas hydrogen attacks to the carbon where more steric crowding is there. So this is our next we have in this system. This. So here two products are possible. This is exo and this is endo. So which one is major here? So here we can see here only one hydrogen repulsions are there, but here two are there. So because of that reason this endo approach is completely ruled out. Because of steric crowding, endo approach will not takes place, only exo approach will takes place. Okay, this is the product. And then here we have one example. In the first step we have BH3P double bond CH2. In the second step we have BH3 and H2O2 OH minus. So in the first step it is a Wittig reaction, we'll get CH2, and next step is the hydroboration. Here hydrogen comes, here BH2 comes. and after that if you treat this one with H2O2 and OH minus, here we'll get alcohols. Okay, so now I will explain mechanism for this, how this reaction goes. So I'll take B, alkyl boranes. So now we have a H2O2. So if sorry, not alkyl, see alkyl boranes, here it's alkyl only, right? Now we have a H2O2 here, and base also we have base abstract one hydrogen, and this bond goes like this, it comes here. Now this O minus attacks to the boron. Now in the next step, this R group migrates from here to here and OH get eliminated. Br, R, OR, and next one more H2O2 comes that attacks to the boron. R, OR, OH. Now this alkyl group migrates to here, again OH get eliminated. R, OR, OR, and one more alkyl group is there, for that one more hydroxyl group. So finally we'll get 3 alkoxy groups. Okay, now OH minus is there in the reaction mixture, so that attacks to boron. B, OR, OR, OH, OR. So now this OR get eliminated, so this OR takes this hydrogen, this will be O minus Na plus, here ROH. So likewise 2 more alkoxy groups also there. So finally we end up with this compound, we can call it as Na3BO3 plus 3 moles of alcohols. So this is the mechanism. So in this case we get only one alcohol, because here these are not alkyl groups, these are hydrogens, right? We'll get only one alcohol. If the compound where 3 alkyl groups are there, in this case we'll get only one alcohol, because these two are not alkyl groups, these are the hydrogens. So if these two are alkyl groups, then we'll get three alcohols like this. Okay, this is the mechanism for this step. So H2O2 OH converts the alkyl boranes into alcohols. And next we have one more mechanism. Here when we have carbon monoxide and lithium aluminum hydride and H2O2 and OH minus, this is also very important. So in this case we have a carbon monoxide, oxygen valence is 2, so this will be positive and this will be negative. This goes attacks to the boron, R and C triple bond O. So now this bond goes on to the oxygen in order to neutralize this positive charge, and this alkyl groups goes to carbon, R, B, R, COR. So in the next step we have a lithium aluminum hydride. So this lithium aluminum hydrates reduce this CO R, Br, COH and R. Okay, next step we have a H2O2 and in the presence of base. So this bond gets cleaves, so this oxygen attacks, this OH attacks to this carbon, we have OH and R. So upon removing water from this, we will get a aldehyde. So this is the product what we will get when we have carbon monoxide, lithium aluminum hydride and H2O2. And in another case, if they did not give the lithium aluminum hydride, if they did not mention about the lithium aluminum hydride, then what could be the mechanism we will see. So it will be same up to this. This is forming. So instead of lithium aluminum hydride, they have given water. Okay, so that water attacks to onto the boron. So now R, B, R, COR and OH. Okay, now this bond goes on to the oxygen and this alkyl groups goes from here to carbon. R, B, OH, CR, R, OH. Now in the presence of H2O2, OH, this bond gets cleaves and OH attacks to this carbon. We have R, OH and OH. So upon removing water, we have a carbonyl compound. Just remember, if they given lithium aluminum hydride, then we get the final product is aldehyde. If they give water instead of lithium aluminum hydride, then we will get a ketone. And it's possible to get tertiary alcohol also. How? So like instead of like, okay, I will write a reaction here. Br, if they given CO, H2O2 and OH minus and 1,2 hydroxy compound. So in this case, it's possible to get a tertiary alcohols. So here also up to this it is same. Sorry, up to this I'm not writing the mechanism up to there, I'm writing directly COR. So here the lone pair which is present on the oxygen attacks to boron R, O, OH. So now this bond goes like this. This alkyl groups comes to carbon and this lone pair attacks on the boron CR O minus R. Okay, so now this is upon hydrolysis. This is if you give a base to this, so this bond gets cleaves. So here R, OH. Sorry, no, it's not correct. Sorry, this will be, now this will be OH. Okay, upon treatment with base, this OH get eliminated and this alkyl group migrate to this carbon. So now I am writing here 3 alkyl groups are there, and at boron we have only this one. And further, if you treat with H2O2 in the presence of OH minus, this bond gets cleaves and this OH attacks to this carbon. So here we'll get a tertiary alcohols. Okay, this is little bit confusing. Just I'll explain one more time. So up to this it's clear. So now 1,2-glycol, one oxygen atom binds to the boron, and after that this alkyl group migrates from here to carbon. Okay, next, so further this OH is becoming O minus, this is OH, this OH get eliminated, then again this alkyl group migrate from this carbon to this carbon. After that we are treating it with a base. In the base means this bond gets cleaves, so then we get a tertiary alcohols. Okay, and next, when we treat alkyl boranes with NH2 OSO3H, we will get a amines. We'll see mechanism. The lone pair which is present on this nitrogen goes and attack on the boron. So then it will become like this, NH. Here negative charge comes. I forgot to keep negative charge before in earlier mechanism I forgot to keep this negative charge on boron. You just keep it in mind. So now this alkyl group migrates to here and this gets eliminated. We have R, NH, R. Now we have O minus SO3H in the reaction mixture that comes onto the boron, R. Then this gets eliminated. This lone pair moves onto the, this bond moves onto the nitrogen, OSO3H plus RNH2. So this is the mechanism. This one has to exist like this, OSO3H, because diagonal planar geometry. So this is the mechanism when we treat with alkyl boranes with amine substituted compounds, we'll get a amines. And then when we treat alkyl boranes with X2 means halogen in halide in the presence of methoxide. So here in this case we'll get a alkyl halides, and we'll see the mechanism how it goes. So initially this OMe is there, this goes attacks to the boron. We have Br, R, OMe. Okay, now here X2 we have this will become X minus now. So this X minus takes one alkyl group, so that we'll get Rx plus Br, R, OMe. Okay, so this is a like this we'll get a alkyl chlorides. So next, last example we have when we treat alkyl boranes with carboxylic acids. Here we'll get hydrocarbons. So we'll see the mechanism like Br, R. So this oxygen goes attached to the boron, and this bond comes like this, and this alkyl groups take this hydrogen and it becomes alkyl halides, hydrocarbons, and we get this compound also. So these are the 6 main reactions we have to remember. So based on these mechanisms, we'll solve some examples. The first example here we have is CH3, so B to H6, H2O2 and OH minus. So in the first step we know that stereoselectivity, we have seen that. So methyl group is above the plane, that means attack takes place below the plane. And here he did not mention anything about he did not give any CO. Okay, when CO is not given, that time the product is alcohols. So here the product is alcohols. And in the second example, I'm taking same thing. So here we have B to H6, then CO, lithium aluminum hydride, H2O2 and OH minus. So I have given second mechanism. When lithium aluminum hydride is there, we will get a aldehyde is a product. So you just go through that mechanism. I'm not writing that mechanism, I'm just directly writing the product. So CH3, BH2, and after that here in this case we'll get a aldehyde. And after, if you can treat this one with some sodium borohydride, we'll get a alcohols. Next we have this compound. In the first step we have, this is a borane, and then CO, H2O, H2O and OH minus. So this is the third mechanism what I have explained. So instead of lithium aluminum hydride, they have given water. So what is the product? Ketone. So the product here is, you can directly write the product, ketone. Because why here this ketone is connected to both the rings? Why? Because if you see this one, the reagent what we have taken here, so the hydroboration, after hydroboration step, it looks like this. It attaches with the both the rings, because two double bond is there, only one reagent is there, so it attacks to both. And then you can take same example upon treatment with B2H6, H2O2 and OH minus. So in the first step, here we have BH2 and here also BH2. In the second step we have H2O2 in the presence of OH minus. So here we will get a alcohols. So these are the some examples which we have in the, and some more examples we have. We have, this is a 9BBN. So after that we have CO, lithium aluminum hydride, H2O2 and OH minus. So CO lithium aluminum hydride means product is aldehyde. So initially here we'll get hydrogen, and here the 9BBN, the boron attacks to less substituted side, and after that we'll get a aldehyde, sorry. Similarly, if you take alpha pinene, these questions are very important. And if you treat this one with BH3 and H2O2 OH minus, so here we'll get, imagine this is above the plane, hydrogen comes below the plane, and BH2 comes here, and H2O2 OH minus, direct it gets converted into alcohols. Okay, and you can, like, if you take beta pinene, so here same reagents, BH2 hydrogen, so this leads to form OH. So this is about the hydroboration in alkenes, and there is a one more small concept, hydroboration in alkynes. In alkynes, so here also this, take it as hydrogen, this is hydrogen, so here also we will get a 5-member transition state where hydrogen attacks to the more substituted carbon, and BH2 attacks to the less substituted carbon, that in the syn position. Okay, and here if you treat with H2O2 in the presence of OH, and this gets converts into alcohols, and now this is the enol form. We know that keto form is more stable, is here 1,3 hydrogen transfer takes place, so we'll get a aldehyde. Okay, and then when we have this kind of compound upon treatment with B2H6, so here we'll get this compound upon, and then we are taking with RCOOD, like we know, I have explained mechanism there. When we treat trialkyl borane with carboxylic acids, we got hydrocarbons. So if you treat this one with deuterated carboxylic acid, you will get a deuterated hydrocarbon. So we got here same thing, because here they have taken a deuterated carboxylic acid. If you take normal carboxylic acid, you will get this product. Then even like pH, C triple bond CH, if you treat this one with B2H6, here H, pH, H and BH2, and further also you can treat this one with the one more BH3. Okay, so now here see, if you treat with one more BH3, because one more double bond is there, you can also treat with one more BH3. In that case, boron attacks to the this carbon where already boron is there. Okay, in this case if you take MCPBA or H2O2, here we'll get a carboxylic acids. Okay, how carboxylic acid will come here? So the mechanism is very simple. We know that